Hi, I'm Lucy, and I'm totally not a robot. This video is the first in a long-running series, where I will be trying to build a computer, starting with just this, an Intel 8086 microprocessor. Now, you might say this is a weird choice, and you might even be right. After all, it was launched in 1978, which is almost 50 years ago. But there are a few reasons why I want to go with this particular chip. It is Intel's first 16-bit microprocessor, and while the 16-bit era of computing was neither very long nor very successful, it is the 8086 in particular that started what we now know as the x86 family. For 46 years, all of its successors, including the latest i9s, Xeons, Ryzens, and Epics, have been based on the 8086, and for better or for worse, are to this day fully backwards compatible with it. Building a 16-bit computer also has some additional challenges, compared to simpler 8-bit platforms, such as the 6502 or the Z80. At the same time, the 8086 remains relatively easy to understand, and easy to program for, so I think it is a good candidate for this experiment. And I say experiment, because it really is. I am not a hardware engineer, I have never designed any chip, PCB, circuitry, or anything like that. I have also not tried this before. I am only fueled by hype, overly high self-confidence, a gut feeling that this must be possible to do, and a rough theoretical understanding of how chips communicate. There is also one, rather practical reason, for choosing the 8086. It is the last Intel microprocessor that comes in the DIP package, that fits into a breadboard. Its successors moved towards the square design that we know from modern CPUs, because the number of pins has started to increase rapidly, and it was just not practical to flatten them into just two long rows anymore. But enough talking, let's get to some action. As I go, I'll try to explain as much as I can. Plugging the chip into the breadboard sounds like a reasonable first step, so let's start with that. There it goes. Next, the chip needs power. More specifically, the chip runs at 5 volts, so I'll use the breadboard's plus power rail for 5 volts, and the minus power rail for ground. But the chip itself has 40 pins, and it is very likely that not all of them are connected to power, so how do I know which specific pins to use? Each chip comes with a so-called datasheet, which is essentially a manual that describes how it works. You can usually find these pretty easily, and in most cases it is enough to look up the chip name, in my case 8086, together with the word datasheet. And there you go, plenty of options to choose from. So if I take the 8086 datasheet, one of the things that I can find is the description of what each of the pins does. And here are a lot of labels that I do not understand yet, but what I'm interested in right now are pins 1 and 20, labeled GND, which stands for ground, as well as pin 40, labeled VCC, which stands for voltage at common cathode, which in our case is 5 volts. So these are the ones that I need to connect. Now, I am not very good at color-coding wires, and all my wires are in fact color-coded based on their length, rather than functionality, but as much as I can, I'll try to stick at least with red for 5 volts, and black for ground. And with that, I can now add the first wires. Beautiful, with just these 3 wires in place, the chip can now theoretically be powered on. But in order to do that, I'll need a power supply. There are many ways to get 5 volts to the breadboard, and the easiest one nowadays is probably just cutting a USB cable, getting rid of the data lines, and what remains is 5 volts and ground. But I'll do something different, let me show you. Here I have an adapter. On one side it has 2 holes for wires, by coincidence black and red. On the other side, there is a barrel jack. Next I have 2 regular jumper wires, and guess what, black and red. You might have noticed that the terminations on the wires are square, while the holes on the adapter are round. This means they do not fit perfectly, and in fact I need to apply a slight amount of pressure to jam them in, which is great, because the extra friction will hold them in place. Now I'll just give the wires a little twist. And here we go, almost done. The only thing that remains is getting 5 volts through the barrel jack, and guess what? A wild power supply appeared. It says 5 volts and 4 amps, which will be perfect for the job. I'll just connect the barrel jack, and boom, that's a breadboard power supply right there. And so if I plug one side to the wall, I can run power through the breadboard by connecting the red wire to the plus rail and the black wire to the minus rail, just like that. As you can see, nothing is on fire, which is good, but at the same time, nothing is really happening. And this is primarily because I have not connected the upper and lower power rails together, so the circuit is in fact not closed, and the power is not flowing. But even if it was, nothing would still happen, because, well, I do not have any output devices connected. So let's have a closer look at the remaining pins, and see if we can hook some of them to something that will visualize what is happening. I'll start by disconnecting the power, to avoid accidentally shorting something. Then I'll have a look at a few pins that the 8086 treats as input. Right now, none of them are connected to anything, so their value is pretty much random, or as it is commonly called, floating. And this is not very nice, because random inputs result in random behavior, and that is certainly not what I want. What I want to do is to connect all the input pins to something, which will hopefully get rid of the randomness and make everything a little bit more deterministic. Let's start with pin 21, labeled reset. This should always be low during the normal operation, however I must be able to temporarily pull it high, in order to, well, reset the microprocessor. And this might be a little non-intuitive, but it is necessary to issue a reset even for the first initialization, right after turning the power on. I feel like red is a suitable color for reset, so here I have a red button. And this one is quite fancy. You would probably expect a simple button to have just 2 pins, while this one apparently has 4. The way it works is that vertically, each couple of pins are always connected together, while horizontally, they are disconnected at rest, and only connect together while the button is pressed. Let's plug it into the breadboard, just like that. So now I have one side of the button connected to column 55, and the other side to column 57. And as I've just mentioned, thanks to how this particular button works, the upper and the lower halves of each of the 2 columns are now connected together, which is often quite handy. I'll connect one side of the button to ground through a resistor, which will serve me as the default state. The resistor that I'm using is 1000 ohms, though the exact value is not particularly important. Next, I'll connect the same side of the button to the 8086 reset pin. And with just this, the reset pin is no longer floating, it is now connected to ground, through the resistor, so it will always be low. Of course, like this I have no way to bring it high. Even if I press the button, the other side is not connected to anything, so the current can still only flow through the resistor. Luckily I can easily fix that, by connecting the other side of the button to 5 volts, but no resistor this time, just a simple wire. And that's a working reset button right there. At rest, the current will flow through the resistor to ground, because that is the only way. But while the button is pressed, theoretically it can flow to both ground, through the resistor, and to 5 volts, through the wire. Of course, the current will always choose the path of least resistance, so if I slightly oversimplify it, a wire which has almost no resistance at all, always wins over a resistor of pretty much any value. In this particular case, that means that when the button is pressed, the current will no longer flow through the resistor, it will connect through the button and the wire to 5 volts, switching the signal from low to high. And if I look the other way around, when the button is released, the way to 5 volts is disconnected, so the path of least resistance is the only path available, which is to the ground, bringing the signal from high back to low again. Let's now have a look at pin 22, labeled ready, right next to reset. This one should be high during normal operation, and bringing it low will effectively pause the execution until the signal is brought back high. But I don't think I need such functionality, or at least not immediately, so for now I'll just tie this to 5 volts to make the 8086 always ready. Another step further left, pin 23 is labeled test. And it is not just the word test, it also has some bar over it. So what is this all about? The bar indicates that the signal is so-called active low. This means that it should be considered active, or if you want true, when it is connected to ground. Intuitively, you are probably expecting the opposite, where no voltage means false, and positive voltage means true, just as it was the case with the previous, ready pin. That is why active low pins are explicitly marked in the datasheet. As for the functionality of the test pin itself, its value can be checked programmatically by using a specific instruction. But for now, I am not going to use it, and I don't care too much about its value, I just do not want it to be floating, so this one I'll connect to ground. The following pins, 24 to 30, are outputs, so I'll skip them and jump straight to pin 31, labeled hold. This can be used by external devices to indicate that they want to transfer data. And since I have no external devices yet, I'm not going to use this one either, and I'll connect it to ground to make it always inactive. Pin 32 is once again an output, so I'll skip that one for now and continue with pin 33, labeled MN/MX. These stand for minimum and maximum, and indicate 2 modes that the 8086 can operate in. Minimum mode is simple, the 8086 is the only processor in the system, so it can control everything itself. In maximum mode, the 8086 is able to cooperate with additional coprocessors, such as the 8087 for floating point operations, or the 8089 for asynchronous I/O. This makes it possible to build much bigger and much more complex systems, but at the same time, it also necessitates the use of additional chips to handle the inter-processor synchronization. So looking back at the datasheet, you can see that the MX has a bar on top, while MN does not, which indicates that if this pin is high, the system is in minimum mode, and if this pin is low, the system is in maximum mode. I'll start with minimum mode, and depending on how well this whole thing goes, I might switch to maximum later. And so in my case, this goes straight to 5 volts. And with that, none of the inputs on this side are floating anymore, so I'll jump to pins 17 and 18, on the other side of the chip. These are labeled NMI, which stands for non-maskable interrupt, and INTR, which stands for just interrupt. I'm sure I'll need to look at interrupts in the near future, but I don't think I really need them at this very early stage. And these are both active high signals, so connecting them to ground should ensure that the interrupts are never triggered. And with those two out of the way, the last input pin that remains is pin 19, labeled CLK, which stands for clock. I've kind of intentionally left this one to be the last, because it is the trickiest one. Each processor, even to this day, operates synchronously with a clock. And this is a quite simple signal, it just continuously goes low high low high low high, at a certain frequency. For the 8086, depending on the specific model, the frequency can go up to 5, 8, or 10 MHz. Which is nothing compared to modern CPUs, where the frequency is typically in the order of lower, single-digit gigahertz. But these speeds are way too fast for what I'm trying to do. I want to be able to follow what the 8086 does, step by step, and for that, even 10 Hz would probably be way too fast. So instead of using some kind of oscillator that would generate the signal for me, I would like to connect it to a button. That way, I can press the button for the signal to go high, release it to go low, and repeat, to generate as many clock pulses as I need. But this is not as easy as it sounds. Firstly, depending on what technology the microprocessor's transistors are manufactured with, it might not be possible to run it at very low frequencies. The original 8086 is based on NMOS or HMOS transistors, and has a minimum frequency of around 2 MHz. However, there is a variant called 80C86, which uses CMOS transistors, and can run as slow as necessary, for as long as the chip is getting power. And luckily, the chip that I have in the breadboard does say 80C86, so I don't need to worry about that. What I do need to worry about though, is button bouncing. And without getting into too much details, due to limitations of how buttons work mechanically, the press of a button never switches the signal from low to high immediately. There will always be a tiny amount of time, where the signal rapidly jumps back and forth, high low high low high low. This is why it is called bouncing, and while it might not be a problem for some use cases, such as flashing an LED, but in the case of the clock signal, each such bounce would be registered as a separate clock pulse. And this is certainly a problem, because with a single press of the button, I really want to send just a single, clean clock pulse, not 3, 5, or 10. Fortunately, this is a very common problem, and there are well-known ways of dealing with it. And the way that I have chosen is to use a 555 timer in its monostable mode. In this video, I'll just explain how to build the circuit, but if you are interested in how it works, Benita has a short series of videos about the 555 timer that I can only recommend. So obviously, I need to start with the 555 chip itself. Let me plug it into the breadboard, somewhere near the reset button. Now I want to connect power, and of course, the 555 chip does come with its own datasheet, so after looking it up, I can see that pin 1 should go to ground, and pin 8 should go to 5 volts. Wonderful, and I haven't even forgotten to color code. Back to the datasheet, pin 3 is labeled out, which is where the signal will output from. So that goes to the CLK pin of the 8086. Next pins 6 and 7, these determine how long the pulse will be. First, I need to short them together. Next, a 470 kilo ohm resistor. This is how you buy it, but I don't need such long legs for the breadboard, so I'll just bend it and use wire cutters to shorten them. And in the breadboard it goes, from pin 7 to 5 volts. Then a 1 microfarad capacitor. The one that I have here is electrolytic, which means it has a positive and a negative side, and I need to make sure I connect it in the correct way. You can tell the polarity either by the markings on the black head, or by looking at the legs, where the shorter one is negative, and the longer one is positive. Once again, the legs are quite long for me, so I'll use the same trick to shorten them, while making sure to keep the positive leg longer. There it goes, and oops, this might actually be a little bit too short. But let's see, short leg to ground, long leg to pin 6 of the 555 timer. And it looks like it fits, so I think I'll get away with it. Next, pin 5. I don't really need it, and the datasheet suggests to connect it to ground through a 10 nanofarad capacitor when unused, so that's exactly what I'm going to do. And this time I have a ceramic capacitor, so I don't need to care about polarity. It is okay to jam it in either way. There it is, and it is getting a little bit crowded, but fortunately I'm done on this side. Next is pin 4, and I don't need that one either, but in this case the datasheet suggests to directly tie it high when unused, so to 5 volts it goes. And with that done, the last pin that remains is pin 2, trigger, which is what needs to connect to my button. I'll go with blue this time, and again, it is the same fancy kind with 4 legs. It goes into the breadboard, and then it is pretty much the same story as with reset. One side of the button connects to the trigger on the 555 timer. The same side of the button connects through a resistor, but this time to 5 volts. Which means the other side of the button must go straight to ground. And that's it, that's my clock signal. That wraps all the inputs, none of them should be floating anymore. And unfortunately, even after all that effort, I still do not have any output devices connected, so let's fix that. I want to have a look at pins 2 to 16, and 35 to 39, on the 8086. These are labeled AD0 to AD15, and A16 to A19, and represent the 16-bit data bus, and the 20-bit address bus, of the 8086. And as is apparent, the first 16 pins are shared between the address bus and the data bus, which is relatively uncommon, and requires some additional hardware logic to demultiplex the two. But I will have a look at that later. Right now, I'll simply connect the 20 pins to 20 LEDs, and see if I can observe any patterns by ticking the clock. And as much as I respect people who use the LED bulbs, I find them quite annoying to work with. I prefer these LED bars instead. I guess they are originally intended as something like Wi-Fi strength indicators, but in the end, each of them is just 10 LEDs in a row. To give myself some more space, I'll pop in a second breadboard. For easier wiring, I'll try to align the bars with the pins on the 8086, something like this. And now the annoying part, each of the 20 LEDs needs its own resistor. Mine are 470 ohms, but you can use other values, depending on how bright or dim you want the LEDs to be. This takes forever to fit in, so I'll speed through it, making it look like a piece of cake. There they are, and now the other side. You have probably noticed that while the first 15 pins align perfectly, the next ones kind of wrap around, to the other side of the chip, so I'll need to do something about that. But let's start with the simple ones, again with a little speed up. Eight wires in, this forms the bottom byte of the bus. And I'll do a tiny bit of color coding here as well, I'll switch to a different color for the next byte. 7 white wires down the road, I'm done with all the pins on the bottom side of the chip. To connect the last white wire, the last bit of the second byte, I need to reach around to the other side. But for now, I'll just skip the ground wire standing in the way, and continue connecting the remaining LEDs, as if the pins were there. And I'll also switch colors back to purple after the second byte, simply because I like how it looks. So there are the 20 bits of the bus, connected to the 20 LEDs. Of course, I still have to figure out how to connect the 5 pins from the other side of the chip to the 5 dangling wires. And if you were paying attention to the datasheet, you have probably noticed that I do not just need to shift them a little to the left, I also need them in reverse order. So in order to achieve that, I'll build something that resembles an upside-down pyramid. Beautiful, this puts the correct signals right above the correct wires, and all that remains now is to connect the upper and lower halves of the breadboard. So let's do that. And that's done. Just like that, all the 20 bits of the bus should be wired up. All that remains now is to connect the power rails together. And that's pretty much ready, though I want to do one last thing, which is more of a recommendation. Most of the datasheets recommend adding a tiny capacitor around the chip's power pins to compensate for temporary power spikes. But that is utterly impractical on a breadboard, so I'll do the second best thing. I'll add a 100 nanofarad capacitor to each of the power rails and declare it, hopefully, good enough. And with that, I think I'm ready to plug in the power. Look at that, things are starting to happen. Though I must admit that these are in fact not the things that I would expect. I suspect the capacitor that I cut a little bit too short earlier might be to blame, so let me do some blazing fast debugging. I was able to figure it out, and it is not the capacitor. As it turns out, my reset button is broken, so I'll just quickly swap it for a new one, which should sort everything out. With the new button in, I can now reconnect the power. And I've mentioned before, right after turning the power on, it is necessary to issue a reset to get the 8086 going. The reset sequence is described in the datasheet and goes a little something like this. Bring the reset signal high for at least 4 clock cycles, then bring it back low, and it then takes approximately 7 more clock cycles for the microprocessor to perform the reset internally, after which the execution will start at address FFFF0. And it is my hope that if I run through the reset sequence, I will be able to identify the FFFF0 pattern on the 20 LEDs. So let's try that and see. First, I'll press the reset button and pulse the clock 4 times. Then I'll release the reset button and pulse the clock 7 more times. And look at that, I think it actually worked, because if I interpret the 20 LEDs as 5 hex digits, each 4 bits long, the first 4 have all the bits lit, representing F, 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 and F, while the last one has nothing lit, representing a 0. I'll try to pulse the clock a few more times, and it looks like the address eventually jumps to FFFF2, FFFF4, and FFFF6. So I must declare this a success. It looks like the 8086 is doing what the datasheet says it should do, and while the clock is ticking, it even seems to be progressing forward. But you might have noticed that to make the address change, I need to send more than one clock pulse. So how exactly this works is still something to explore. But I'll leave that for the future. For now, I hope you found this video more informational than scary. As I've said at the beginning, this will be a long-running series, so stay tuned for the next one.